Our first speaker is Krishna Gummadi, Faculty and Scientific Director at the Max Planck Institute for Software Systems. He also holds a professorship at the University of Saarland. His current projects focus on understanding and building social computing systems that, among other things, tackle challenges associated with enhancing fairness and transparency of machine data-driven decision-making. Krishna's papers have received numerous awards, including Test of Time Award at ACM SIGCOM and IIIA ICWSM. He received the ERC Advanced Grant in 2017 to investigate foundations for fair social computing. Krishna Gummadi's talk is titled Engineering a Fair Computing-Mediated Society.
Thanks for the introduction. Welcome, everyone. So I was tasked with giving an overview talk on algorithmic fairness, and that proved too much of a challenge to do in 15 minutes. So what I thought I would do is share with you a few things that I wished that I knew when I started working on this topic of algorithmic fairness 5 to 7 years ago. So the basic premise with which I'm going to start my talk today is that we are living in a computing-mediated society. And what I mean by this is that for thousands of years, we as humans, whenever we were changing and growing and building and tearing down and rebuilding our societies, we would always interact directly with each other. We would negotiate, fight, whatever it was just between humans. Whereas now, today, we have computing technologies and AI agents that are increasingly becoming the mediators of all our societal interactions. And in the process, they're also evolving and changing our societies at a very rapid and disruptive pace. So I'm going to use the word fair in a very broad way. In fact, I'm going to use it in the same way as John Rawls, a very famous legal, political, and moral philosopher uses it, which is justice is fairness, and fairness is being just. So it's about engineering a just computing-mediated society. So just to take a few examples of how computing is mediating our society today, if you think about digital public spaces, these are things like Facebook, YouTube, TikTok, Wikipedia. You have search and recommender AI algorithms, which are increasingly regulating what sort of information we produce and how we share it with others and what information gets popular and so on. Next, if you think about digital marketplaces, by this I mean e-commerce platforms or sharing economy platforms, gig economy platforms, freelance platforms, Uber, Airbnb, Amazon, or even Kickstarter, what have you. On all these platforms, increasingly you see match and market making AI that is connecting up producers and consumers of goods and services, and in the process determining what prices we pay. Finally, if you think about risk prediction AI, which is increasingly underlying many different decision support systems in a variety of domains, be it judiciary, policing, social welfare benefit distribution, recruiting, banking, insurance, and medicine. In all these domains, once again, you have AI systems that are assisting and nudging experts as they make decisions that critically affect our lives. Now, there is an important, but it's a subtle but very important distinction that I feel is important, that I would like to make here between AI models and the platform architectures that give agency to those models. And oftentimes this distinction is not made. You can think of platform architectures as the ones that make the AI models come alive. These are the hardware and the software that goes with it. You could also think of them as essentially providing a framework or setting the ground rules for how these AI models interact with other AI models as well as with humans. And this distinction is quite important because sometimes when we think about unfairness, some of them are caused by the AI models, and some of them are caused by the platform architectures. And it's also possible that sometimes the deficiencies of one could be addressed by being careful about how we are engineering the others. Now, pretty much everybody in this room, I'm sure, is aware of the big promise and the peril of this AI-driven computing-mediated society. So I'm not going to belabor this point beyond pointing out the types of perils that I would think of as those related to unfairness are things like this, or an article that talks about e-commerce platforms being opaque, or articles like this, or this, or this, or this. Okay? Now, what I'm going to argue is that if we want to engineer a fair computing-mediated society, we need to think of these two distinct problems. One of engineering of AI models, and the second is engineering of platform architectures. So let's quickly go through each one of them. First, let's start with engineering AI models. Now, over the last 2 decades, if you think about it, AI became dominated first by machine learning models, and then machine learning itself, in turn, got dominated by deep learning models. And deep learning itself, more recently, began to be dominated by foundation modeling. Now, each of these revolutions in AI modeling has changed very significantly how we engineer or how we program these AI models. For example, traditionally, if you went back to 60s, AI used to be just computer programming, where you would just tell the computer how to solve a particular problem. Now, with the advent of machine learning, this style of imperative programming, where you tell how the problem should be solved, became one of declarative programming, where you only specify the goals of the program, but you let the machine search for the optimal procedure. Now, this is a dramatically different way of programming, and that has consequences. And similarly, when traditional machine learning moved towards deep learning, what used to be called as feature engineering became replaced with representation learning. So traditionally, machine learning engineers would very carefully specify what features of the data should be used for solving the task. But with deep learning, once again, we leave it to the machines to find out what representations or what features to extract from the data, which they then use to solve the tasks. And then again, in traditional deep learning, it feels strange to call something that was only 10 years ago as traditional, but in traditional deep learning, you would train a model for a specific task. And if you wanted to adapt it to a different task, you would actually do task-specific fine-tuning, where you would change the model weights and so on. Whereas with foundation models, where you're training it on the entire world's data, the expectation, and to an extent what is being borne out in experiments, is that you could do zero-shot prompting, where you just tell the model what you want it to do, or just give a few examples, which is called few-shotting, and then voila, it works across a wide range of tasks. Now, in some sense, this sort of benefits do go with some downsides as well. So first, for example, the moment traditional AI began to be dominated with machine learning methods, immediately the problem of fairness came up. This is because now all of a sudden, if you're just specifying the goals for the model, you now have to find a way of specifying all the fairness desiderata as goals for the model. How do you express the need to follow laws and social norms and other sorts of things as objectives for the machine learning models? So this became a fundamental problem. Next, when deep learning came about, all of a sudden, explainability and robustness of the models have become a very big problem. And in fact, I would go as far as to claim it as a foundational problem, in the sense that there may be fundamental limits to what we can explain about these models. The reason being, if the models are picking up their own features that they find useful for a task, it's almost impossible to guarantee that these would align with humans. In fact, every experiment that people have done shows that there is always some form of misalignment, and there may be fundamental limits to what extent we can explain these models or how robust they are. And finally, with respect to foundation models, they're very exciting, but I think it would be fair to say the one thing that characterizes them is a complete lack of foundations. We often today study the behaviors of these models, and we are happy when the behaviors align. but we barely understand the cognitive, from a cognitive perspective in terms of how the information is being stored or retrieved or organized or being processed by these models. In fact, we keep coming up with innovative, cute terms like what used to be a robustness problem now becomes a hallucination in the context of foundation models. Now, there's a lot of interesting work being done to address some of these challenges, and I do, like for example, people are trying to come up with new machine learning methods and model training, and I do think some of these could be mitigated to an extent, but I don't believe that fundamentally you can solve these problems. So as a result, one approach would be to guardrail the AI model deficiencies, right? And today you have a variety of ways in which you could guardrail these by monitoring inputs and outputs of these models, whether at training time or inference time. And you do this at the level of individual data points or at the level of groups. And then you do this with often having humans in, under, and over the loop. And what I mean by this is where humans are either collaborating with the models, or they're overseeing the models, or they are being controlled by the models themselves. And then you have a variety of different types of explanations, like causal and counterfactual explanations, and based on the extent to which we have access to the model, whether it is a white box access, which means you have complete control over the model, versus gray box and black box access, where you have different amounts of transparency into how the models are working. Now, this guardrailing is now, when we start talking about guardrails, we are already going in this direction of like putting some computing architectures around the models, right? And this brings me to the second point, which is about engineering the platform architectures that give agencies to these models and potentially guardrailing them. Now here, without a deep discussion, I'm going to claim that there are three main types of aspects that one should be worried about when you think about platform architectures. The first is related to how the data of all the stakeholders of the platform is being gathered and being processed over the infrastructure, and whether this data and infrastructure is being centrally managed or being managed in a federated way or being done in a very decentralized way. And this has big impact on the privacy of the stakeholders. The next set of problems are related to how trust is built into the, trust is being built between the different stakeholders. Is it based on some centralized identities, or is it based on a web of trust, or is it based on some sort of proof of work that the stakeholders who are part of the system show? And also, this is related to the incentives that they have to behave or misbehave in the system, which in turn ends up determining very critically the accountability of the stakeholders. And finally, of course, there is a big issue of stakeholder autonomy and how the stakeholder preferences can be aggregated to arrive at consensus for governance. Now, the tragedy today is if you actually look at most of the platforms that are very popular today, that are giving agency to these AI models, they're all under centralized control, oftentimes by a single company where there is one dominant controlling shareholder even. And you often lack transparency. Now, given this, this almost makes the case for regulatory oversight. That is, it calls for examining by regulators whether these societal scale platforms pose systemic risks and cause harms. In fact, many countries around the world, including European Union, is going in this sort of a direction, given the situation today. You have a variety of different acts like GDPR, you have DGA, which is a Data Governance Act, and then you have the Digital Markets Act and Digital Services Act, and finally you have the AI Act as well. Now, if you think about, and if you read many of these acts, they are about assessing and preventing these harms. But here is an important thing to observe. These acts provide fantastic policy frameworks that has been arrived at in a democratic way. But what they don't solve is yet, or what we do not have yet, are the operating frameworks. And what I mean by operating frameworks is how do you operationalize, audit these platforms, and enforce the aspirations of these laws and regulations, the policy goals. By operationalization, what I mean is literally how do you quantify and determine whether or not some platform or some AI model is adhering to these policy goals. And this is where a lot remains to be done. In fact, this is a fair bit of, this is also a place where technical people, computer scientists, need to work closely with legal scholars as well. Just to give you a quick example of this, suppose let's take this goal of non-discrimination, which is one of the many policy goals of Digital Services Act. If you want to operationalize non-discrimination, it has been studied quite a bit in social sciences, moral philosophy, and so on. Here is a sort of an intuitive definition of non-discrimination. Discrimination happens when you wrongfully impose a relative disadvantage on persons based on their membership in some salient social group. This is probably a definition most of us would agree upon. But the critical thing is, how do you operationalize this definition? And what I mean by operationalize is, how do you formally define and interpret these notions like wrongful imposition, relative disadvantage based on salient social group? In fact, this is where a lot of technical work in the community also kicks in. And here I'm just showing various different ways in which one could interpret these terms of non-discrimination. And in fact, sometimes not distinguishing between different types of interpretations is what leads to these sorts of problems where there was this very famous tool for estimating recidivism risk that was actually originally designed to conform with one of the interpretations, but it failed the second interpretation and therefore was understandably accused of creating bias. Now, if you start thinking about operationalizing this non-discrimination at the platform level, like online advertising, this becomes even more complex because all of a sudden now you have different subcomponents of the system. Like, for example, if in online advertising, it can be discriminatory because of the way in which the user interests are being inferred, or because of the way advertisers are targeting the users, or because of the way in which the platform inferred the relevance of an ad for the users, or how the ads are competing in auctions. These are all different components of a very big system, and it's really hard to distinguish. It's really hard to understand the effects across the board. So as a result, you might well have a situation where individual components, maybe even if you made them non-discriminatory, the system as a whole could be discriminatory. And this brings me to the last point that I wanted to make, which is sometimes it might be useful to think about end-to-end arguments in system design. These are the arguments that are widely known to people in the distributed systems and networking community, where they say when you have a complex system with multiple subcomponents, and if you want some property like fairness or some functionality, it's important to look at from an end-to-end perspective and not just get caught up in just making individual subcomponents fair. And in this particular context, what this would mean is there a way in which the ads, when they're delivered to the users, can be made non-discriminatory? And here I just wanted to note that recently there was a settlement that Facebook had with the Department of Justice in the US, and I was reading through the settlement, and one thing that I found very heartening is that they actually ended up with a solution that was an end-to-end, satisfying the end-to-end principle in the sense of guaranteeing non-discrimination at the end. So with that, I just want to, this is my final slide, to conclude that if you are thinking about engineering a fair computing-mediated society, it is worth thinking about engineering of the AI models. And there you have two options. We can try to design fair human-aligned AI models, but given that some of the foundational challenges, we may have to think about guardrailing them. And then the second thing is, in an ideal world, we would all be using more open, decentralized platforms. But if we're living in a world of closed, centralized platforms, we may need regulation. And maybe if in the future if these regulations are different for different places, that might force a certain amount of decentralization of the platforms. Thank you.
Thank you. Let's take a question. Yes, back there on the right.